In this video, we're going to study the limits and end behaviors of arithmetic and geometric sequences. My first sequence is an arithmetic of t sub n equaling 3n plus 8. I set my value of n equal 1 so I can find my first term. Since 3 times 1 plus 8 is 11, there it is, my first term. What I'm also going to do is provide you a graphical representation of the sequence. So here's my value of n as 1, and here's the height at 11. Now what I'm interested in doing is taking a look at what happens at the second, third, and fourth term. But in actuality, when you're studying the limits, you're actually looking to see what would happen to these values as n increases without bound. We might even say as n approaches infinity. Well, in this case, because I've put 2 in for n, I notice I get 3 times 2 plus 8 is 14. I'm not going to give you a play-by-play. Let's just take a look at what happens to the values of t sub n as n increases. So now we're up to 10, and we can see that's going to 38. And if we get up to a value of n equaling 20, we're already up to a height of 68 as the graph is changing over here. Now, I could keep going, but I think it's pretty obvious that this is going in a straight line, because it is a linear relationship, and it's going to increase without bound. This sequence diverges. Something that is divergent, and it can be a sequence or series, does not have a finite limit. As we keep going all the way out to, in this case, my 51st term, over here you'll see that we have a notation that's written in terms of limits. That's what LIM is. I would say that the limit as n approaches infinity of the quantity 3n plus 8 goes to infinity. And that makes us a divergent sequence. Now, I'm going to tell you, it's not going to really make a difference what kind of arithmetic sequence you have. They're all going to diverge. Here we have an arithmetic sequence whose common difference happens to be negative 7. You can see just by the pattern of dots that this is going to approach negative infinity. It still is divergent. Now, sometimes students get a little confused because they think it should stop at a different value. But let's go back to the 10th term. All right? What happens is that you have to remember that n keeps increasing without bound. So as we move to the next term, now it's hitting a value of 8, and now it's going to 1, and now it's just going to keep on going and go negative 6 and negative 13 and so on. And as we continue the dots on again, you can see it goes back to a negative infinity. So as I pull up all these different arithmetic sequences, all of them will approach infinity or negative infinity. So as you can see, all arithmetic sequences who do not have a common difference of 0 will go to either infinity or negative infinity. So they all diverge. Let's move on to geometric sequences. We'll begin with t sub n equaling 6 times 3 raised to the n. We'll plug in 1 again for n. 6 times 3 is 18. First term is 18. We'll plot the point. What we're going to do is we're going to move on to n equals 2. So 6 times 3 squared is 6 times 9, which is 54. Or you can remember that we're multiplying by 3. That's our common ratio. So if we again want to do this a third time, 6 times 3 cubed is 6 times 27. It is also going to be the same as taking 54 times 3. In both cases, you get 162. So if we just want to keep saying we're multiplying by 3 each time, you will notice that we're working our way upward. Now you have to pay close attention to the y-axis. We're already up into the 15,000s. All right, and as I keep going with this sequence, you'll see now I'm up to 120,000 over here on the side. So this is curving upward quite quickly, to the point where I think it's safe to say that this is a sequence that diverges. And we can say that its limit as n approaches infinity of 6 times 3 to the n equals infinity. Now we can have sequences that go up, and we can have sequences that decrease without bound. And in this particular case, we can say its limit is negative infinity, but again, a divergent sequence. There is another type of divergent sequence where we can't write the limit as infinity or negative infinity. Let's take a look at it. Here we have the sequence negative 4 times negative 3 raised to the n. If we plug in the value of n equals 1, we get 12. But if we plug in the value of 2, we're going to go negative 4 times negative 3 squared. Now, negative 3 squared is 9, so negative 4 times 9 is actually negative 36. We've gone from having a positive value to a negative value. If you realize that negative 3 is your common ratio, we just take negative 36 times negative 3, and we're going to be back to the positive side of 108. But you'll notice the dots keep getting farther and farther apart as we move through the sequence. Now, if we looked at the absolute value of the individual terms, yeah, sure, we could say that they're increasing. But that's not fair to describe the sequence that way, because first we were positive, now we are negative. And that doesn't mean we were always decreasing, because the next time we're going positive again, so that'd be increasing, and then we're decreasing. And so we might want to say that this is going to infinity when we look at this particular value of n, but the next time we might want to say it's going to negative infinity. When it's alternating like this, you can't even say a limit equals infinity or negative infinity. All we can do is say that the limit does not exist, or DNE. It's still divergent, but we can't be any more specific than saying it just does not exist. Let's just make sure we're clear here. You may have had a limit that had gone to infinity. You may have had a limit that ended up going to negative infinity. The definition of divergence is it does not approach a finite limit. These are infinite limits. Mathematicians like to be as specific as possible. So we can say it's going to the positive infinity. We can say it's going to the negative infinity. But there's still limits that don't technically exist. Now, D and E is when you can't just even come up with something as clear as that. And that's really the difference. In the end, they're all divergent. Don't overthink it. So now I have a sequence that's 200 times 4/5 raised to the n. If I plug in the value of 1, 200 times 4/5 is 160. If I multiply by 4/5 again, I'll get 128. And I'll multiply by 4/5, and I'll either get the fraction 512 over 5, or I'll get 102.4. As I keep going, I recognize that my numbers keep getting smaller and smaller and smaller. But unlike arithmetic, they're never going to go negative because I'm never multiplying by a negative number. In fact, what they begin to do is they begin to level out. And as you can see, these numbers keep flattening out to what looks like the x-axis, which means it's going closer and closer to 0. And that's the limit of this particular geometric sequence. It converges. It has a finite limit, 0. It keeps approaching and getting closer and closer. Let's go look at another one. The first term of this sequence, 3 times 2/3 to the n, is 2. As I multiply by the common ratio 2/3 each time, you'll notice again that the numbers keep getting smaller and smaller and smaller. In fact, again, we would say that the geometric sequence here converges to 0. What would happen if I would be coming up from, let's say, the bottom? Maybe I start with a negative value, negative 160 times 1/2 raised to the n. So I'm coming up from the bottom. I'm starting at negative 80. But as I multiply by 1/2, I'll notice that my terms, if I'm ignoring the negatives, again, look at the absolute values, are getting smaller and smaller and smaller. So in this case, my limit seems to be converging to 0. Is this always the case if you have a geometric sequence that converges? The answer is yes. Even if it's as fun as this one, 8 times negative 1/2 raised to the n, first term is negative 4. But because I'm about to multiply by the common ratio negative 1/2, I know I'm going to alternate back to the positive side, giving me 2. But then I'm going to multiply by negative 1/2 again and alternate back to the negative side. And I'm going to bounce between the positive and negative. But in the end, although I'm bouncing above and below the line, it's essentially flattening out to the point where I will also say it converges to 0. If you're willing to overlook geometric sequences whose common ratios are either 1 or negative 1, and I'm willing to do so, then we can put these geometric sequences into 2 categories: those that diverge and those that converge to a limit of 0. And all you need to study, or all you need to examine, is the common ratio for each of those sequences. If the absolute value of the common ratio is greater than 1, the sequence will diverge. If you're going to multiply by 2, or multiply by negative 3, or multiply by positive 4, or multiply by negative 6, you're going to have a divergent sequence. On the other hand, if you have a common ratio whose absolute value is less than 1, meaning it falls between negative 1 and 1, but remember we're ignoring the endpoints, numbers like negative 3/4, positive 2/5, 0.6, negative 0.1, they will all converge to a limit of 0. So to summarize, if you have an arithmetic sequence, tell me it diverges. It might go in infinity, it might go in negative infinity, just tell me it diverges. When it comes to geometric, look at the common ratio, and then tell me it either diverges or it converges to a limit of 0.